Hey everyone, welcome back to the channel. You are watching Build AI with Sandeep. Have you ever wondered when we pass different vectors to the neural network, the training becomes unstable, the training becomes slow and even gets stuck. Do you know why does this happen? Well, it is because our vector values are not balanced and the model gets confused. That is where layer normalization comes into picture. In the today's video, we are going to understand what is layer normalization. I'll explain you this topic simply with examples and formulas so that you can easily understand the layer normalization topic. So first of all, so first of all, I want to discuss why do we need normalization? Simply normalization. So in neural networks, when the output of the neurons becomes very large or very small, the model faces problem of slow learning and unstable gradients. Some values explode, some values vanishes. This is called exploding and vanishing gradient problem during the backpropagation. Okay, let me clarify this statement. When bigger number multiply by bigger number, suppose this multiply, so this is even more bigger number. So you all know in neural networks there is multiple dot product operations and vectors multiplied with vectors. If vector values are very large, then after multiplication it will become more very large. So this is exploding gradient problem. Exploding gradient problem. The second one is if the value is very small, 0.001 multiplied with 0.0001. So it will become very small value. Then model get confused. And in this case, this is vanishing gradient problem, and our neural network stops learning because 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 this is very small value, and when we do the differentiation, when we do back propagation, apply chain rule, so it will become zero. The output value is become zero and our model stops learning. So these are two major problems. So we need a method that keeps our vector values balanced, centered and stable. We want these three conditions to satisfy in our vectors. Okay, so that is why we are doing normalization. So now comes to what is layer normalization. So let me explain what is layer normalization. So I already pasted the definition that layer normalization makes the values in a layer. And what is layer here? Layer is basically a vector more stable by adjusting them so that they have a mean of 0 and variance of 1. I hope you all know what is mean. Mean is the average of n values, and variance is something that tells us how spread our data is. So variance is basically tells us the spread of the data. Okay, so let's suppose we have a vector zero point 0.2, 1.4 and 5. Okay, so after normalization we will get an output vector that have mean equal 0 and variance is equal to 1. Okay, we use this notation to mu for mean and sigma square for variance. Okay, so layer normalization in our case, in we are learning neural networks. So we took the output of the self attention. I hope you all watched my last video. In my last video, I explained self-attention in a very super simple way. So output of self-attention, we saw that for each word, cat, drink, milk, for each word, we get a vector. We get a vector of size 3, of dimension 3. So now we apply layer normalization on each vector. layer norm layer norm on each vector, and after that we will get the normalized value. And why we are doing normalization? Because we want that our model does not faces the problem of vanishing and exploding gradient problem, and our gradient updates become stable, and the speed of the training becomes increase speed of the training increase, performance increase of our model. That is why we are doing layer normalization. Okay, so now we understood how we are doing normalization, layer normalization, and layer normalization is applied on features, not on batches. Since in language modeling there are sequences that have different sizes, so we are not using batch normalization here. We are using layer normalization, and layer normalization is applied on each vector that represent that word. Okay, and how, now coming to how we are doing layer normalization. So let me take you to the layer normalization slide. So yes, now I pick an example vector. I pick an example vector that have three values. Okay, so to normalize value, we use something called as Z score. Now you all must be thinking, what is Z score? So Z score is nothing but it is telling us that the value, the point, how many standard deviation away the specific point is away from the mean. Okay, so you can think like this. So there are points. Okay, this is our mean. So let's take 1.84. Okay, so I will tell you after this explanation completes using this normal distribution. Okay, so for now, uh, I'm telling that to normalize the values, we use Z score. Okay, and in Z score, the X is basically our these values, these three values. Okay, X represent these three values. And what is sigma? Sigma square is basically, this is variance, and mu is our mean. So first we calculate mean of the values. So we have three values, 1.84, 2.51, and 0.33 divided by n. This is the formula of mean. Basically, I is equal to 1 to n xi divided by n. This is the formula of mean. Okay, and that is what we used here. So we get a mean of 1.56. Now we compute sigma square. The formula of sigma square is mentioned here. So we use mean in the formula of variance. So using this formula, we compute our variance, and variance is basically 0.8332. So standard deviation is basically square root of variance. Okay, so we do the square root of this value and we will get this 0.913 value of our standard deviation. Now we use mean and standard deviation in our Z score formula. We will calculate Z score for all three values, Z1, Z2, Z3. 0.307, 1.04 minus 1.35 will be our values. Now let's come to this normal distribution. What I was trying to tell you, that the mean here is 1.56. Okay, 1.56. Now this 0.307, what it is telling, what this value is telling us, that okay, in this vector, the 1.84 value is basically 0.307 standard deviation away from the mean. Okay, so 1.84 value is basically the distance 0.307 standard deviation. So this Z score is telling us the exact thing. Okay, so we compute Z score for all three values and we will get our normalized vector. Okay, so this is how we are doing normalization. Now in layer normalization that we have in our transformer architecture, we are doing one more thing. And what is that thing? That our final normalized value, normalization, y normalized value is basically gamma x plus beta. So we use gamma and beta additionally after the normalization for each vector. Okay, so we will do this thing for three times: gamma 1, beta 1, and y1. y2 norm gamma 2 x1 x2 plus beta 2, gamma 3 norm gamma 3 x3 plus beta 3. So these values are our final output of the layer normalization layer. So now you all are thinking that why we used gamma and beta when we already did the normalization. So to answer this, we are passing. So basically, sometimes model lose the original information when we do multiple vector operations. So our neural network loses original meaning of the vector. So that is why these gamma and beta are learnable parameters, and we allow our model to all learn its scaling and shifting on its own. Okay. So these gamma and beta are learnable parameters, and we allow our transformer architecture, our model, to learn its own scaling and shifting on its own. What is scaling and shifting? You know the graph. Okay. So this gamma makes the upward and downward, this x value, and beta makes the shifting horizontally. Okay. So this is what we are doing in the layer normalization layer. Now, now I want to tell you that why transformers love layer normalization, because it works perfectly for the natural language processing and sequential tasks. Layer normalization does not depend on batch size, and also it helps our attention output more stable. So layer normalization makes the training more faster and more stable, makes the gradients smoother. That is why GPT, BERT, T5, Llama, and all major models use LayerNorm. And now, where is LayerNorm used inside transformer? So, after self-attention, before residual connections, we use the layer normalization. Okay, sometimes it is pre-layer normalization and sometimes post-normalization. Now, to now I'm this is a small topic and I'm wrapping up. To give you a summary of what we have learned, layer normalization helps keep vector values balanced. It normalizes across batch features, not batches. It improves stability, training speed, and performance. And that is why it is used heavily in transformers. Now you understand layer normalization clearly. In the next video, I'll explain the feed-forward network with examples, vectors, and full calculation. If this helped, comment LN clear. I'll reply to you personally. And don't forget to like, subscribe, and share with your AI friends.